you can take it from here.
Okay, awesome. Thanks, everybody. So, my name is Marlon. I'm a senior researcher at IMEC in Belgium, and I teach at Ghent University. My research area is broadly software delivery and software trust in cloud and to devices. And so initially that was a lot of configuration management, Kubernetes, but now recently we started a whole new research track on WebAssembly. As part of my research, I also do a lot of open source and standardization work as part of Ubuntu, as part of the W3C and the Bytecode Alliance. But I'll talk a little bit more about that later in the presentation. So WebAssembly for Edge and IoT devices. In my presentation, I will start with just a general introduction of WebAssembly. I know that some of you already know what WebAssembly is, so it might be a little bit of a repeat, but some of you might not have a good idea of what WebAssembly is, so I wanted to start with just general WebAssembly introduction. And so the reason why WebAssembly is so interesting. This is basically the creator of Docker, who a few years ago, back when Twitter was still Twitter, created a tweet saying that if WebAssembly and the WebAssembly System Interface existed in 2008, they wouldn't have needed to create Docker. And so obviously, when this person says something like this, I was also very interested to see like, well, what is up with WebAssembly? Why is this web technology suddenly an alternative to Docker? So let's take a look. First, what is WebAssembly? WebAssembly itself is binary code. They also say it's a compiler target. You compile your code to a virtual CPU, the WebAssembly CPU, and the bytecode that you get, it can't run on an actual CPU. It can only run inside of a WebAssembly runtime. Initially, that was the browser, but then people also wanted to use WebAssembly on servers, and so the Node.js runtime also implemented WebAssembly. But now the recent iteration of WebAssembly and why we're so interested in it is the new generation of WebAssembly runtimes like WASM-time. These runtimes, you have a couple of different ways in order to run WebAssembly just in time, which is basically the runtime is compiling the WebAssembly code to a CPU code at runtime, basically while the program is running. And this often use something like LLVM in the backend in order to then cross-compile WebAssembly to the native architecture. You can also have ahead of time compilation. This is basically where you compile WebAssembly to native code beforehand, or you can have an interpreter. An interpreter is basically the runtime looking at each and every byte in the WebAssembly binary and then doing an action that corresponds with that byte. The WebAssembly runtime is often called a virtual machine, and this is correct. This is actually completely correct. WebAssembly is running inside of a virtual machine on a virtual CPU. And so why WebAssembly initially existed was to support basically any language in a minimal runtime. And that minimal runtime then being something that the browser can support. It's completely cross-platform like any web technology. It's sandboxed by default, which is incredibly important in a browser space. You don't want one tab when you have one tab open with a random website and then another tab open with your banking information, you don't want the WebAssembly of that one tab to be able to snoop your banking information from another tab. And it has near native performance. And this was also a big reason to create WebAssembly. So if you look at the initial use cases for WebAssembly, it was all browser-based. Either it was because companies had a large C++ code base, but wanted to provide certain functionality of that code base in WebAssembly, in a browser, basically. They wanted to provide a large part of that functionality in a browser. And so instead of having to rewrite all their code in JavaScript, they just compiled it to WebAssembly to then run that in the browser. A second browser use case is basically compute intensive subtasks. When we talk about codecs, compression, filters, inference, encryption, those are all tasks that are very, very CPU heavy. Which can really benefit from running it in WebAssembly as compared to JavaScript. Then, however, very recently, a new use case appeared: Edge and IoT devices. Basically, using WebAssembly as the last plugin model that you'll ever need. It's already used heavily in plugins for Kubernetes, for example, in order to do policy verification by running WebAssembly next to an open policy agent, for example, as part of a database in order to create custom query logic inside of a database, but also as an alternative distributed compute model. So this is basically an alternative to containers, basically, an alternative to containers and to virtual machines. Because as you might know or might not know, when we talk about serverless, from a user perspective, this seems like a completely different technology than virtual machines. But if you go to AWS and actually look at their servers, every serverless function is running in a separate virtual machine. This is basically because Amazon simply does not trust software isolation. Amazon does not trust that the Linux kernel is safe and secure enough in order to actually separate tenants. And so even if you're using serverless, it's actually running inside of a virtual machine. So because of that, there's a large basically a large incentive to look at alternative compute distribution models that have the same security as hardware virtualization has, but that is a lot more performant than hardware virtualization. And so if you see this move to the edge and IoT use case, your first question is obviously what changed? What happened to get WebAssembly from a purely browser technology into edge and IoT devices? And it's basically the introduction of the WebAssembly System Interface. WebAssembly System Interface, this is in the context of a WebAssembly application talking to the outside world. And with the outside world, I mean a WebAssembly application opening a file, downloading a file, opening a TCP IP socket, doing threading, contacting USB devices and stuff like that. How this worked initially was with a legacy system interface called Emscripten. And what Emscripten actually does is it uses the existing JavaScript API of your browser. So your WebAssembly code itself, every time it needs to send a packet to another device or something, it calls a JavaScript function in order to then call this JavaScript Emscripten API of your browser. Once WebAssembly was initially ported to the server, specifically for backend server development in the Node.js runtime, they simply ported this JavaScript API and ported it to servers, and then added a few additions, for example, in order to open local files, something that's not allowed in the browser. This JavaScript API is, first of all, incredibly inefficient because you get from literally a bytecode format, CPU optimized code that then suddenly has to call JavaScript functions in order to do basic functionality. This API is gigantic because it basically contains the last 20, 30 years of World Wide Web development and has to be compatible with that entire legacy. And it's not secure, but maybe I should add a disclaimer there. When I'm talking about it's not secure, I'm not talking about the browser side. This API, when it's running inside of a browser, this is one of the most secure APIs that exists in the world. because Google, Microsoft, Apple, they're all constantly doing a lot of work in order to make this API incredibly secure. And we've gone up to a point where people don't think twice about opening a random website and then opening their banking website in another tab. There are some people I know that use different browsers for banking and not, but I know very few of those people. So it's very secure in the browser. However, this port of these APIs to serverless, to servers, this port actually, this port is not secure. This port basically by default allows any application to access any files. And then there's a lot of work that has to go into actually securing these APIs. So the solution was for the W3C to create from the ground up a completely new API, the WebAssembly System Interface. This is a new syscall interface built for speed, security, and cross-platform support. It's standardized by the W3C WASI subgroup, and most of the implementations are built by the Bytecode Alliance, together with many non-browser partners, including Cloudflare, Fastly, also some IoT developers like Siemens, and then some virtualization providers like VMware. And so it's this specifically. It's not WebAssembly on itself that is an alternative to Docker containers, but when you combine WebAssembly with the WebAssembly system interface, then you get a highly performant, highly secure bytecode format with a highly performant, highly secure system API. And so it's this that is driving the revolution that is pushing WebAssembly into a whole bunch of use cases where normally containers were the state of the art. So at this point in my presentation, I sometimes get the question of, okay, but like this all seems very familiar. I've heard this exact same story with Java. So what is the difference between WebAssembly and Java? First of all, there's many similarities, both in how they are designed low level and in the use cases. Java is targeting this use case of write once, run anywhere. It has architecture independent bytecode with some other languages also running inside of the same Java virtual machine. There are some companies who use JVM on microcontrollers. There are some companies who use JVM in browsers, but ultimately, most of those use cases have failed. Good luck trying to run a Java application in your browser in this day and age. And it remains a single vendor runtime for a single language family. So the WebAssembly is basically a reimagination of this exact same idea, but learning from the past 20 plus years of JVM experience. WebAssembly, it has been created as a compilation target for all languages. And the compilation target itself is standardized by a completely independent body, the W3C. In contrast, JVM itself is way too reliant on a single vendor, is not really standardized. There's the de facto standard, which is the implementation, and is way too focused on a single language family. As an example, JVM is incredibly opinionated. For example, your language basically has to be able to understand what a class is and what a garbage collector is in order to make it easy to port your language to the JVM. A second issue with or a second advantage of WebAssembly is that it's sandboxed by default with capability-based access to the outside world. The issue with JVM is that they have too much access to the underlying operating system, and this is both a problem for security and for portability, because a lot of applications that run inside of the JVM, because they have such intimate access to the underlying operating system, they write code, the developers write code that only works on one of the underlying platforms or only works on one of the underlying operating systems. Also, JVM basically assumes that all code is trusted. Whereas WebAssembly is sandbox by default. And then the final big difference between WebAssembly and JVM is that WebAssembly has software delivery baked in. Things like streamability, like hot plugging, these are things that are baked into WebAssembly, while JVM is mainly focused on the traditional applications consisting of a single static monolithic application that's already on the user's machine. So each of these differences, there are sometimes research projects, sometimes very complicated production frameworks out there in order to solve all these problems more or less for JVM. But as we can see simply by looking at the current use cases for JVM, none of these frameworks, none of these solutions are both very performant, very user-friendly, standardized, backwards compatible with a whole bunch of stuff. And WebAssembly basically delivers all these very, very well. So then, WebAssembly for edge and IoT devices. It's the topic of my talk. In order to explain why we're looking at WebAssembly for edge and IoT devices, I'll just give one fact to you. The average lifespan of cars in Europe is 30 years. In Western Europe, it's a lot less. In Eastern Europe, it's a little bit more than 30 years, but the average car in Europe is only scrapped after it has lived for 30 years. So 30 years ago, we were all using Windows 94 or maybe some esoteric Unix variant. I think Linux just existed, was barely usable probably at that time. I was 2 years old, so I have no idea how Linux looked at that time. But all the chips that are in those 30-year-old cars, the software on those chips was back then compiled on probably proprietary compilers running on Windows 94. If you're lucky, some of these compilers still work on Windows XP. But a lot of these automotive companies have virtual machines with Windows XP in order to be able to update some of the software on some of these devices. So yeah, how do you update the software on a car that uses a compiler for Windows 94? Some use virtual machines. Some require hardware updates every time you do a software update, just buy new hardware. But very often the answer is they just don't update it. These are some statistics. For example, annual number of CVEs in automotive companies worldwide is rising incredibly quickly. Part of the reason why this is rising quickly is not because they are creating more vulnerabilities, but is more because we are now really finding them. The industry as a whole has basically woken up to this reality of our cars are actually getting hacked in the real world. We need to find and fix security vulnerabilities, but at the moment there's a lot of them. Then if you take a look at a lot of the software that's running inside of these cars, a lot of the software hasn't had any updates for over 10 years. And so if you look at OpenSSL, for example, an OpenSSL instance, an OpenSSL implementation that hasn't been updated for 2 years is a big issue. An OpenSSL implementation that hasn't updated for 10 years, but it's just a block of cheese. It's full of holes. It's incredibly easy to hack it. But this is what these cars are driving around with. This is what these cars are using to secure connections. A lot of these very, very highly critical vulnerabilities are the software that has these vulnerabilities is still being used in cars. And as a result, car thefts are rising almost every single year. It's up to a point where basically kids are teaching each other on TikTok how to hack cars with some common vulnerabilities. So software updating. Compatibility with very old platforms, with very old systems, with very weird architectures. This is a problem that we've already solved. As a field, this is a problem that we've already solved with web browsers. Web browsers basically always download the latest version of the application and are incredibly backwards compatible. So why not use this technology, this WebAssembly technology? Why not use it as the narrow waist of automotive software? So what we mean with that is you have this incredible diversity in applications that are being written for automotive chips. You have an incredible diversity of different programming languages, and they all compile to WebAssembly, a standardized common set of binary code. And then underneath the WebAssembly layer, you again have this wide variety of all different kinds of hardwares, operating systems of all different ages, of all different versions. And WebAssembly is basically the thing that connects these together. This is a slide I shamelessly stole from a presentation from Bosch last year at WASMCon in Seattle, I think it was, just to show you that like this is not something I'm not the only person who sees this potential. I'm not the only person working on this. We have a lot of the automotive and industrial IoT chip builders who are really looking into this and who are currently doing a lot of the enablement work in order to make this future a reality. And so the advantages summed up are basically you have binary device portability across all instruction set architectures on any platforms. You compile it once and it can run on any of these chips. You have support for much more programming languages and language interoperability on embedded devices. In some way, the second bullet should simply be support for more than simply C. Because for most of these embedded chips, your choice is to either use C or use nothing. And then if you use C, you're often using like sometimes a proprietary or a custom version of GCC in order to compile your software for these devices. It's definitely not a pleasant developer experience. It also gives you forwards compatibility with newer application tool chains, because these newer compilers, they can still compile to WebAssembly, so their code can still run inside of these WebAssembly runtimes. And it's completely secure, completely sandboxed execution of software where other solutions like containers do not fit. One of our prototypes used to run on a microcontroller that has 265 kilobytes of memory. This is crazy. Like these devices are too small to actually run a Linux kernel, but you can run WebAssembly containers on them. And most importantly, WebAssembly has all these advantages while still ensuring support for pre-existing software, compiling pre-existing code to WebAssembly to run on these devices is incredibly easy and often requires minimal changes. And you have near native efficiency in execution and compilation. In some of our benchmarks, we even see slightly faster than native execution. We think this is because the just-in-time compiler can optimize a little bit better to the specific CPU that it is compiling to. And the just-in-time compiler also has more information in order to optimize your code, because it also has information about how your code is currently running. And because of that, we see either very close to native performance or in maybe a few percentages better speed than native. So what are we specifically doing with WebAssembly? The first thing we're doing is what I call cyber-physical WebAssembly. We're building interfaces and support in order to connect WebAssembly applications to the underlying hardware. The goal is to make it possible to use WebAssembly for IoT devices, but that means that you need to be able to change the pins, the output pins on your microcontroller. You need to be able to connect to USB devices from WebAssembly and things like that. The second goal is to have secure drivers that only access exactly what they need. If you have a USB device driver running inside of a Linux kernel, and that USB device driver is compromised, it basically has access to your entire kernel and your entire operating system. However, if you run these device drivers in a WebAssembly container, then if the driver is compromised, then the only thing the driver can access is that specific USB device that the driver has been written for. And it has much higher reliability and robustness by sandboxing components, because one component, one driver can crash without pulling down your entire operating system. And then finally, it also gives you the ability to create portable drivers for any architecture, any platform, and to support newer hardware on older platforms without having to change the kernel that is running on top of those platforms. Let's skip this because this is a much better image of the exact same thing. So how we're doing this is basically hardware WebAssembly system interfaces and componentized drivers. So let's talk about the WebAssembly system interfaces first. That's this part of the drawing. So WebAssembly System Interface is an API standard, a standardized API for how applications can communicate with the underlying operating system. So we've currently created two of those standards, an API to connect to I2C, to the I2C bus, and an API to connect to the USB bus. And then basically the application, the WebAssembly application itself, connects to this API and does certain calls, and then the WebAssembly runtime basically sends those calls to the host operating system and then to devices. However, because these APIs are written as part of WebAssembly System Interface, we get a whole lot of cool functionality for free, like the capability-based security of WebAssembly System Interface. With this, we mean that so if you think about system calls in Linux, if an application is not allowed to do a certain system call, it can still try to do it. It can try to call that system call, and then the operating system basically checks if the application is allowed to do it, and if the application is not allowed to do it, it ignores that call or crashes the application or does something. However, in capability-based security, basically for a WebAssembly application, if it doesn't have access to a certain functionality, then it can't even request access to that functionality. And it can't even try to call these interfaces because it simply has no way to actually call these interfaces. That's a capability-based security. If the runtime doesn't give the application access to that interface, then the application cannot call that interface. However, what we've seen is that you actually need a second layer of security, because in the if we're talking about USB, for example, you might want to give a certain application access to a USB device. Let's say that's a camera, it's a camera, but maybe you only want to give it access to read the camera feed and not to change the settings of the camera. This is something that in terms of capability-based security, the capability is access to that camera. So if we want a more finer grained way to actually mediate what an application is allowed to do and what it's not allowed to do, then we need an additional layer. We implemented this as ACL-based security in order to then filter, even if an application has a capability, to then still deny certain syscalls or syscalls with certain arguments, for example. And then in terms of the the other side of the runtime, so the host component. The host component is basically the platform-specific implementation of that API. So the host component, we have a prototype where where we have a USB implementation that runs on both Windows and Linux. The host component is what's different in these two. The host component on Windows uses the Windows APIs, and the host component on Linux uses the Linux APIs. And that's baked into the WebAssembly runtime. But the functionality, the USB functionality for the host component, for example, is incredibly simple, because the actual, it doesn't actually have a driver. It only needs a driver for basic USB functionality, but device drivers are what's running inside of WebAssembly. That's the additional functionality is what's implemented in WebAssembly. We have a preprint. We've submitted a preprint about this. We submitted this paper to IEEE NOMS, and I just got a message from Michiel van Kenhoven, who is the PhD student working on this, that he also submitted it to ArcSIF, and so probably tomorrow this paper should also be available on ArcSIF as a preprint. This basically explains this entire functionality. It explains all the different ways of access control that we have, and it shows, I think, 3 or 4 proof of concepts running on microcontrollers, running on Linux devices, running on a Windows laptop. And some of the things we do is we are able to have a WebAssembly application that implements a file system driver, that implements a USB stick driver, USB storage driver, and that you can use to send and receive files to a USB stick. We also have a prototype that implements an Xbox controller, so that the Xbox controller driver is written as a WebAssembly application also, and so that application just gets raw access to that USB device. If you look at performance, because I'm assuming that by this time somebody is screaming at their screen, what about performance? Well, in my opinion, performance is amazing. So if we look at the additional latency of a WebAssembly application talking to a USB device versus the exact same code base running natively on Linux talking to a USB device, then we see a round trip time, an additional round trip time latency of 0.007 milliseconds. This is so small that it could very well be no difference. And the reason why I'm saying that there's actually no difference is that it takes longer for a USB device to for a USB hub to basically complete an entire cycle of sending and receiving data than the actual overhead of WebAssembly. So the overhead that WebAssembly has doesn't actually really matter, because the CPU has to wait longer for a response from or has to wait longer until it's allowed to put messages on the USB bus than that it has to wait on WebAssembly. This is specifically for, we started testing this after the application has started up. So with a running application, what is the difference between doing a call via WebAssembly or doing a call via a native application? If we look at throughput, then we see a more significant reduction, although it's still less than 1%. We see less than almost 0.5% reduction in USB throughput from WebAssembly, which in my opinion, like I was incredibly surprised when I saw these results, because this has at least one additional mem copy. Maybe it has 2 additional mem copies that it has to do in order to do this in WebAssembly versus native, but still, like the change is so small. However, we also looked at cold start latency. This is another example where we contact an I2C display. If we look at cold start latency, then we see about 7 milliseconds, but almost that entire 7 milliseconds is spent on starting up the application, and only then does it do something. So let's say you have an application that writes a certain text to a certain display. If you run that application as a binary, and then run that application as a WebAssembly binary, then booting up the WebAssembly runtime, starting the WebAssembly binary inside of the WebAssembly runtime, and then writing to the display, this will give you a total complete extra additional overhead of 7 milliseconds, which if you compare it to Docker containers, this is amazing. This is very small overhead. Docker containers use a lot more time in order to actually boot up and do something. And this is one of the reasons why you see so many companies that are building serverless tools moving to WebAssembly, because a cold start, the difference between a hot start and a cold start is basically 7 milliseconds for easy workloads. And you can even improve this, because this is not an optimized solution. This is also using the JIT compilers. So this is not an ahead of time compiler or anything. Even the compilation, starting the compilation is part of that 7 milliseconds. If you're interested in this work, the top two ones are actual standards, an I2C standard and USB standard that we've created, and that's been accepted as part of the official WebAssembly System Interface project. The I2C standard is currently in phase 2. The USB standard is currently in phase 3, in phase 1. And most other WebAssembly system interfaces are in phase 3. So we hope that by the end of this academic year, we can at least move the I2C standard to phase 3, which will mean that it's ready to be implemented in all compilers and in upstream libraries and stuff like that. We also have an implementation of both solutions. We both have example application that use the interface, so like the application side of the API, and then also the runtime side of the API. The I2C interface, we're building that in collaboration with Siemens, because they're using WebAssembly on some of their microcontrollers, and they have an internal I2C interface to do that, but they're really interested in actually standardizing that interface so that in 10, 20 years, compilers will still be able to compile to their microcontrollers. For USB, we have two different implementations, which during this academic year, we're hoping to merge them into a single implementation. And we also have two proposals in development. Currently, we don't really have anything to show about those two proposals, but we're working on GPIO access for WebAssembly applications and SPI access for WebAssembly applications. And maybe I should add that if you're interested in seeing the driver running inside of WebAssembly, then look at this project, USB WASM. This also has, for example, an implementation of a very, very simple Xbox controller driver running inside of WebAssembly. Okay, so the next thing I want to talk to you about, but I'll go over it very quickly, is we're also working on using WebAssembly to shrink Kubernetes. Specifically, we see a lot of developers that are really happy with the developer experience of Kubernetes, but that also want it for edge devices. The problem is Kubernetes is a very hungry hippo that likes to eat your resources. And specifically, we are targeting reducing the footprint of operators. Operators are plugins for the Kubernetes control plane that manage containers and resources. For example, you have an operator in order to deploy distributed data storage. You have an operator in order to deploy MySQL. They manage quite complex applications. But operators are long-running processes written in Golang. Golang also really likes to eat your memory, running inside of containers, sitting in RAM while doing nothing. So the first thing we did is just run these operators as WebAssembly processes. We do this by having a parent-child situation, basically, where we have a parent operator, and that is the part of the operator that connects to the Kubernetes API to watch resources, and it gets notified when a resource changes. And when a resource changes, it sends that change to the child operator that then processes that change and maybe updates some other resources in order to process that change. Simply by compiling this to WebAssembly and running them all as part of a parent-child operator framework, we were able to make the operators use 68% less RAM. This is mostly due to removing a lot of the duplication that is happening in all these containers normally. But what we did then is, well, actually turn it serverless. Since WebAssembly has startup times, cold start times in the order of milliseconds, we thought, why not just turn off the operator while it's doing nothing? And when a change happens, we boot it up again, it processes that change, and then shuts down again. And in a worst case scenario, we see that it still uses an additional 50% less RAM when we unload idle operators. However, this all happens at the cost of latency. In the worst case scenario, we see that it takes about 10 milliseconds to start up the operator to process changes, which is not a lot in itself. But if you have a chain of 100 operators that all contact the next one and the next one and the next one, then it really starts to add up and you get into latency overheads in the number of seconds. So then finally, I wanted to give a few tips. If you're interested in WebAssembly, if you're working on WebAssembly, what should you look at and stuff like that. First of all, there's a very large community. Standardization happens in the W3C WASI subgroup. Development happens as part of the Bytecode Alliance, and they're specifically building Wasmtime. This is a runtime optimized for cloud and edge computing, and WAMR, WAMR. This is a runtime optimized for edge devices and IoT devices. WAMR is the runtime if you want to run it on a microcontroller, because you can compile it in such a way that it only uses 50 kilobytes of memory, just the runtime itself. But there's a very large and active community on Zulip. You can go to the Zulip of the Bytecode Alliance, where even our students, even our master's thesis students have been able to get very useful help from some of the core developers while they were developing this technology. Then, second one, language support. So this idea of WebAssembly as being a universal bytecode format supported by all languages, we're not there yet. Language support varies a lot between different languages, even though it's improving rapidly, and many of the upstream language developers are integrating and implementing WebAssembly. It's not there yet. If you have a program written in Rust, C, or C++, it will probably run without any issue in WebAssembly. However, if you use Python, Java, or C#, then some functionality will work, but maybe some advanced reflection functionality will not work. However, if you're writing in some other languages like Golang, then even basic functionality will not work, and you need to use very, very specific compilers. Like for Golang, you need to use TinyGo, which doesn't support any reflection, even though most of the Golang standard library uses reflection. So your mileage really varies in terms of depending on which language you use. Second gotcha is the ever-changing landscape of system interfaces. These system interfaces, they are being standardized. But while they are being standardized, they're also already implemented in a lot of compiler tool changes and stuff like that. So at the moment, you basically have three system interfaces. You have Inscriptum, which is the browser one, and this will only run in browsers and in an OTS runtime. You have WASI Preview 1. This is the first preview of the WebAssembly System Interface, which is now considered legacy. You will see a lot of documentation right now actually talks about WASI Preview 2, even though many runtimes and many compilers still only support WASI Preview 1. Then another thing to note is that some runtimes use non-standard dialects of the WebAssembly System Interface, which really means that like you really need to have your language needs to support it, your compiler needs to support it, and your compiler also needs to support the specific dialect that the runtime supports. So it becomes quite difficult to find the right tool chain in order to compile something that runs on the runtime that you want it to run. WASI Preview 2 is supposed to be much more backwards and forwards compatible interface, which currently has been publicly released, but is still being implemented in a lot of compiler tool chains and in a lot of runtimes. WASI Preview 2 is also called the component model. If you ever see that terminology, then they're talking about WASI Preview 2. Third gotcha is the varying support of runtimes. Does your runtime support the system interfaces that you want? I personally recommend using either wasmtime or Whammer. wasmtime supports WASI Preview 2 and the component model. Whammer only supports WASI Preview 1, specifically in order to be able to be as small as possible to be able to run on these microcontrollers. I cannot recommend Wasmer and Wasm Edge. I think Wasmer is a non-ideal choice to make because it uses a lot of non-standard tool chains and a non-standard WebAssembly System Interface implementation. Wasmer is basically creating a sort of island ecosystem of tools and runtimes that all work within each other, but that are highly or that are not completely compatible with the actual standards that the W3C is making. And then Wasm Edge, Cloud Native Compute Foundation project, I don't recommend using that simply because it's super slow. And our benchmarks show that it's super slow. Let me go to the next slide here. You see that's the mean execution time for 10 runs of a certain application. Wasm Edge just it's so incredibly slow. And we showed these graphs to the Wasm Edge developers, and the Wasm Edge developers basically said like, yes, this is expected because Wasm Edge currently only supports an interpreter mode. If you actually want performance, then you can switch to the beta version of their just-in-time compiler mode, but they're not completely sure whether or not they're going to make that a full part of the project because Wasm Edge basically targets places where you cannot do just-in-time compilation. There's a lot of places where you cannot do just-in-time compilation, like in iOS applications, for example. You're not allowed to do just-in-time compilation, or in certain platforms, you're not allowed to execute memory. But then if you look at other runtimes, so here you see this is the execution time for a native binary. This is the execution time for the same binary in wasmtime. This is all very, very close to each other. The only one that's significantly faster than native is Whammer. But Whammer, yeah, it's incredibly optimized, but it's also written in C. So it's a little bit maybe less trustworthy than the other ones that are written in Rust. I have to add though, I didn't include them here, but these performance benefits always happen at the expense of RAM. From our benchmarks, you more or less can expect a WebAssembly application to use about double the RAM that a regular that running a regular application can use. It depends on if your application is using a lot of data, like whether you use data as inside of WebAssembly or outside of WebAssembly. That doesn't really matter. There's no big difference there in overhead, but your application itself, your binary, basically, when your binary is in RAM, it will take up twice the amount that it would take up if you're running it native. And then finally, I just wanted to make a little bit of advertisement for our workshop. In January, we close a call for papers for our WebAssembly Cloud and Edge Shaping the Future of Computing workshop, together with the Bytecode Alliance and as part of the Elastic project. Please take a look at that. We're part of IEEE NOMS conference in Hawaii, which is probably a little bit unfortunate for us Europeans. But yeah, take a look at that. So it took a little bit longer than I expected. So I'm not sure if there is a lot of time for questions anymore.
That's fine, Marlene, no worries. I mean, thanks a lot for your presentation. Very, very interesting. Maybe we have time for 1 or 2 questions. If someone has any questions, please unmute yourself and ask. If not, I will ask. Okay, maybe I can start. So one, I would say curiosity. I mean, I have many from the slides, but I mean, let me try to look for things in the future. How do you see WASI evolving? I mean, do you see it as there will be some sort of like core syscalls that will be supported and some optional ones that will be added as we start to consider new applications? Yes. How do you see it?
That's a very good question. Yeah, and that's also part of the switch from WASI Preview 1 to WASI Preview 2. In WASI Preview 1, it was basically you have WASI, and you either have support for all the syscalls or you don't. While with WASI Preview 2, they included this concept of worlds. And a world is basically a collection of interfaces. And so one of the worlds they have is a CLI world, which is basically a Unix style, all the Unix style interfaces that you need in order to run a CLI application on a host. And this includes then things like standard in, standard out, being able to open files using Unix sockets and things like that. And so the idea is basically that as a developer, you target a certain WASI world with your application, and then you just need to find a runtime that supports that world. And that's how every time there's new interfaces that will come into the picture, some of these interfaces will be added to some of the existing worlds. Other interfaces will become part of new worlds. For example, I'm expecting that my interfaces that we're building, USB and I2C, will become part of like an embedded world or something that then developers can target, and then they can just see if the runtime supports this world, and if it supports this world, then it will support your application.
So what you envision here is that certain additional functionalities would be grouped together inside the wall, and that providers will have some sort of support for different walls, and then you will choose the provider based on whether it supports a certain wall that at the same time needs to support a certain runtime.
Yeah.
Okay. Yeah, that's interesting. I have another one. I don't know if someone else wants to ask something. I have another one in slide, I think it was 34, 35. This is a bit more detailed, but this wasn't very clear. Yeah, here. What did you mean by native? What is your native? What do you?
So native is just a binary that's running on the host system. In this specific test, this was on a Raspberry Pi, on a Linux system.
Okay. Yeah, because I was thinking that it would have been nice to see the baseline with a container, I guess, no? And maybe also the
That's true.
the differences between the two main ways of compilation, because this is also something that I'm very curious about. How does this just-in-time compilation affects to this?
So comparison with containers, I don't have that, although I think we are working, or a colleague of mine is working on a paper where they compare it to all different kind of virtualization technologies. In terms of the difference between runtimes, this is work that we will publish quite soon, probably. So here you see some comparison between WAMR, JIT eager, WAMR JIT lazy, WAMR fast JIT, WAMR multi-tier JIT, and then fast interpreter. And so you see interpreter modes are always a lot slower than native, but then we don't see that much of a difference between the different JIT times. And these figures don't include it, but we also did benchmarks with ahead of time compilation. And from our perspective, we didn't see much performance improvement for ahead of time compilation. These JIT compilers seem to be so good and so quick that from the moment your application runs more than a few milliseconds, the overhead of JIT compilation is completely gone compared to ahead of time compilation.
Okay, I see. Yeah, I mean, every time that I see just-in-time compilation, I'm still surprised at this. I mean, of course, there might be good reasons for this to be used, but I also know that in terms of security, it's not a good choice. Typically, I think that there are lots of security defenses that you can circumvent if you start using just-in-time compilation. But
yeah,
not an expert on the topic, but I'm still a bit surprised that this is still used.
Yeah. There is some interesting work that is happening to try to use, for example, Cherry in order to better secure the JIT compilers. But I'm totally not a compiler expert. That's completely out of my depth. I just see the JIT, I see that it works very well, and so I use it. Probably it's not the most secure option here.
Yeah. Okay, so if there are no more questions, I think that we can leave it here. Merlin, thanks a lot for giving us this talk. I mean, it's a relatively new topic for us, so we really learned lots of things from your work, and we stay in touch, right? So we will be
yes
enriched about this topic for sure.
All right, thank you a lot for having me. It's always a pleasure to talk about this stuff.
Thank you. Bye.
Bye.
Thank you, Merlin. Bye.
Bye. Thanks.